another for the negative. So for 3 phases, we will be having 3 into 2, 6 SCRs. Or otherwise, we can have IGBTs, that type of self-commutating devices. So we can use SCR or any of the self-commutating devices. So this circuit is for the using SCR, and another one is for using IGBTs. And for each case, we are having some anti-parallel diodes or the feedback diodes. So that will be used for the feedback of the energy stored in the load to the source. So the energy will be stored in the load. So that will be fed back to the source by using these feedback diodes. So the step is the by means of changing the firing from firing angle or the changing of the input gate pulses from one SCR to next SCR in a proper sequence, we will achieve the steps. So totally there will be 6 steps. So for 360-degree waveform, that is for one positive half cycle, it will be 180 degree. Another for negative half cycle, it will be another 180 degree. So totally full cycle will comprises 360 degrees. So 6 steps into 60 degree per step, right? So for 360 degree, there will be 6 steps for with each step of 60 degrees. So in 3-phase bridge inverters, we will be having 2 modes. There is 180-degree conduction mode and 120-degree conduction mode. So it depends upon the conduction angle of each device. So if an SCR means if each SCR conducts for a 180 degree for a single cycle. So that is called 180-degree conduction mode. And if it is an 120-degree conduction mode for a single cycle, that is 360 degree, each SCR will be conducting for 120 degrees. So these are the circuits. So first one will be using the SCR and diode, and second one is using the IGBT and diodes. And this is the voltage source VS, input voltage source DC, and this is a DC link capacitor. So this capacitor already I have told that is for using this capacitance, we can maintain the constant voltage. So this will provide the constant input voltage to the inverters. So this is a 3-phase load. This may be an any load, that is R load or RL load or RLC loads. And this is the schematic diagram for the 3-phase inverters. So here we are having 3 SCRs in parallel with diodes. For 6 SCRs in parallel with 6 diodes. So this SCR is replaced by this switch, that is single pole single throw switch. Each switch is representing a switch that may be an SCR or IGBT or any of the device in parallel with the diode. So this is a single pole single throw switch. So totally there are 6 switches, and here also the numbering is important. So that is first one here 1, 3, and 5. That is the first one is connected to this is A phase. So here ROAB, instead of ROAB, we are representing it as A, B, and C. So A is the first phase, B second phase, and C is the third phase. So A is connected to the T1, and the second one, the T3 will be connected to the B phase, and T5 will be connected to the third phase, that is C phase. So these odd number devices are connected to the anode of the odd number devices are connected to the positive of the input voltage source. So these are the positive group of devices, that is positive group of SCRs. And here T4, T6, T2. So these devices are connected to negative. One end is connected to negative, another end is connected to the load. So these even numbered SCRs are called as negative group of SCRs, since it is connected to negative. And here we can see the odd number devices are connected between the positive terminal of the input voltage battery and the load. So these are the positive group of SCR, and the lower ones are the negative group of SCRs. So here we can see, so the S1 is connected to positive of VDC, another end of S1 is connected to the load of, another end is connected to the load end. So the odd numbered devices or odd numbered SCRs are called positive group of SCRs, which is connected to positive of the input, and the S4, S6, and S2, that is negative, it is connected to the negative terminal of the battery, it is called as negative group of SCRs. So we can numbering it as 1, 3, and 5. So here 1 plus 3, 4, that is S4, and 3 plus 3 S6, and S5 plus 3 S8, totally 6 switches. So 8 minus 6, that will be S2. So the numbering is also important in this case. And next one is the conduction. So since it is a 180-degree conduction mode, each device will conduct for 180 degrees. So here, what will be the conduction angle means? So the SCR from same leg will conduct at an interval of 180 degrees. That is, if S1 starts the conduction at 0 degrees, since it is the 180-degree conduction mode, it will finishes its conduction at 180 degrees. 0 to 180 degree, the T1 will be conducting. And after that, the T4 will start its conduction at T 180 degree to 360 degrees. So each device will conduct for 180 degree and the devices from the same leg. So this is the A phase leg. So here S1, here it is mentioned as T1. So it can be taken as S1. So S1 will be conducting from 0 to 180 degree. That is positive half cycle. And the T4 will start the conduction from 180 degree to 360 degrees. Similarly, the S3, the conduction difference between S1 and S3 is 120 degrees. So here it is mentioned that is S1 starts the conduction at 0 degree, and the second phase SCR, that is positive group of SCR, S3 starts the conduction at 120 degree, and the third one S5 is starting the conduction at 240 degrees. So the phase difference between this positive group of switches is 120 degrees, and the phase difference between the same leg devices will be 180 degrees. So if this is starting the conduction at 0, and S3 starting the conduction at 120, and S5 starting the conduction at 240 degrees. And here S4 is starting the conduction at 180 degrees. That is, here is starting point is 0. So another phase shift of 180 degree, the S4 will starting the conduction. And here S3 is starting the conduction at 120 degrees. So S6 will start the conduction at 120 plus 180, that is 300 degrees. And T5 will be starting the conduction at 240 degrees. So 240 plus 180 degrees, that will be 420 degrees. So for a single cycle, we have to calculate. So for 420 minus 360, so that will be 60 degrees. So it will start the conduction. S2 will start the conduction at 60 degrees. So these are the conduction sequence for the 6 SCRs. So we have to remember that is for 180 degree conduction mode, each SCR will be conducting for 180 degrees in a single cycle, and the phase difference between the each phases will be of 120 degrees, and the phase difference between the positive and negative group of SCRs will be 180 degrees. So using this, we can see we can draw the conducting sequence. So this is the conducting sequence. So here we can easily represent. That is, first one will be the A phase, and second one will be the B phase, and third one will be the C phase. So we can draw. That is from. So we have to draw 3 lines. So is it viewable? So I'm drawing the lines. Is it viewable in your laptop or mobile? ஹலோ அது வரைகிறது வந்து தெரியுதாப்பா? கண்டக்டிங் சீக்வன்ஸ் வந்து நான் கீழே வந்து ட்ரா பண்றது உனக்கு தெரியுதா? ஹலோ
இல்ல சார், தெரியல சார்.
So directly we can see that is for A phase, the T1 and T4 are the positive group. T1 is the positive group of SCR, T4 is the negative group of SCR. So T1 will start the conduction at 0 degree, and the negative group of the CRE T4 will be starting the conduction at 180 degrees. So T1 will start it from 0 to 180 degree, and T4 will finishes its conduction from 180 to 360 degrees. So this will repeat for the next cycle. So this is second cycle. After 360 degree, it will be the second cycle. So single cycle will be 360 degrees. That is 2 pi. So pi will be 180 degrees, and 2 pi will be 360 degrees. So each cycle will be 360 degrees. So this is for the first phase T1, T4, and each will conduct for 180 degrees. Then next one, see, B phase. B phase, the conducting SCRs are T3 and T6. That is T3 will be positive group. That is odd number will be positive group, and the even number will be negative group. So T3 and T6, T3 positive and T6 will be negative. So T3 will start the conduction at 120 degrees. So the phase difference between each positive group of SCR will be 120 degrees. So T3 will be starting the conduction from 120 degrees, and it finishes from 120 plus 180, that is 300 degrees. So T6 will start its conduction from 300 degrees. So 300 plus 180, that is 480 degrees. So for single cycle, it will finishes its from 360 degrees. That is 300 to 360 60 degree, remaining 120 degree from 0 to 120. So before the T3, the what will be the device has to be conducted is T6. So for 0 to 120 degrees, it will be T6 will be conducting. So we can see T3 is starting the conduction from 120 plus 180, that is 300. It is the finishing point of T3 conduction, and T6 will start the conduction at 300 degrees. For the finishing of single cycle, it is conducting up to 360 degrees. That is 60 degree here it is conducting. Remaining 110 degrees is for previous case, that is the before T3, the 120 degree will be completed. Then next one, C phase, the conducting SCRs are S5 and S2. S5 are the T5 is the positive group, and S2 is the negative group. And S5 or T5 is starting the conduction from 240 degrees. That is T1, T3, T5. T1 0, T3 120, and T5 240 degrees, from 240 to 360 degrees. 240 plus 180, it should be conducting from, that is 240 plus 180, it should be conducting from 240 to 420 degrees. But for finishing of the single full cycle, the 240 to 360 it will be conducting. Remaining 60 degree will be conducting from 0 to 60 degrees. And T5 is starting the conduction from 240 degrees. So 240 plus 180, that is 420. That is after the single half cycle, that is 420 minus 360, it will be 60 degrees. So from the 60 degree point, it will T2 will be starting the conduction. So 60 plus 180, that is 240. The T2 will be conducting. Now we have to make the conducting SCRs. That is for each 60 degree, we have to calculate what are the SCRs that will be conducting. So here we can see for 0 to 60 degrees, the conducting SCRs are 5, 6, and 1. And for this 180 degree conduction mode, 3 SCRs will be conducting at a time. For each 60 degree, 3 SCRs will be conducting at a time, and 2 from either it can be 2 from the positive group or 1 from the negative group, or vice versa. So at a time, 3 SCRs will be conducting. It can be 1 from positive and 2 from negative, or 2 from positive and 1 from negative group of SCR. So for first 60 degrees, the conducting SCRs are 5, 6, and 1. And the next 60 degrees, that is 60 to 120 degrees, it will be 6, 1, and 2. And for next 60 degrees, it will be 1, 2, and 3. So it will be a series. If you look this, it looks like a series, that is 5, 6, 1, 6, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, and 4, 5, 6. And again the cycle repeats, that is 5, 6, 1. That is for the second cycle, that is 5, 6, 1, 6, 1, 2, 1, 2, 3. So this thing you can easily remember, so that it is written like this. That is 5, 6, 1, 6, 1, 2, 1, 2, 3, 2, 3, 4. So for each 60 degrees, 3 SCRs or 3 devices will be conducting. So from this, we have to calculate what will be the output voltage waveform or what is the nature of the output voltage waveform. So we have to calculate two waveforms. That is, since it is the three phase, we have to calculate phase voltage waveform and line voltage waveform. So for first 60 degree, what are the devices conducting? 5, 6 and 1. And here we can see this is step 1 for the 0 to 60 degrees. The devices conducting are 5, 6 and 1. So already I have shown this circuit. So here all the switches are in open condition. And now depending upon the sequence, what are the devices conducting for first 60 degree, 0 to 60 degree, that is 5, 6 and 1 are in closed position. The remaining switches are in open position. 4, 3, 2 are in open position since it is not conducting. And 5, 6 are in closed position since it is conducting for the 0 to 60 degrees. So here we can see 1, 6 and 5. So out of these three switches, the 5 and 1 are the positive group of switch and 6 is the negative group of switch. So the first switch, the 1 is connected to A phase and the 5 is connected to C phase. So these A phase and C phase are connected to the positive end of battery. So this is a diagram that is representing that. A and C. So this is a three-phase load. So this is a three-phase load that is of impedance. So here it may be an impedance or a resistance. So here we are taking it as an impedance, that is Z. That is the magnitude of that impedance. And here we can see 1 and 5 are the positive group of switch. So here A and C phase are connected to the positive terminal of the battery. So A and C are connected to the positive terminal of the battery. Another end of the load, that is this Z is connected to, one end is connected to A, that is connected to the positive end, another is connected to the neutral point O. So A and C are connected to positive and the B phase alone is connected to negative. Since 6 is conducting, the B phase is alone is connected to negative. So B is connected to negative, another end of the Z of the B terminal is connected to the neutral O point. So now we have to calculate what is the voltage across each phase. That is, we have to calculate the VA naught and VC naught, VB naught. So three voltages we have to calculate. This is the phase voltages. VA naught is the voltage across the A phase and the neutral point. VC naught is the voltage across C and the neutral point, and similarly VB naught. So we have to calculate what is the voltage across VA naught and what is the voltage across VC naught and what is the voltage across VB naught. So we have to use the, that is voltage division rule. So voltage division rule. So here it is Vs, input voltage, total voltage is Vs, and here it is divided into two circuits, that is VA naught, VC naught, and another branch is VB naught. So here we are having two parallel, that is Z, two parallel combination of Z. So what will be the equivalent value of two parallel combination of Z? That is Z into Z divided by Z plus Z. That is Z square divided by 2Z. So Z will get cancelled, so that we will get the Z by 2, right? Z by 2. So Z by 2 means, so this is the equivalent impedance across this two parallel combinations. So if we replace this two parallel combination by a single impedance, so that will be Z by 2. So we can redraw it is Z by 2 and here it will be Z. And we have to calculate the voltage across that two branches. Across Z by 2, what will be the voltage, and across Z, what will be the voltage. So we have to use the voltage division rule. So Vs into Z by 2 divided by Z by 2 plus Z. So total impedance Vs into across this, that is Z by 2, that is Vs into Z by 2 divided by total impedance, that is Z by 2 plus Z. So if we simplify that, we will get the voltage as Vs by 3. That is VA naught and VC naught are Vs by 3. And here we have to calculate Vs into Z divided by Z plus Z by 2. So for that we can simplify and we will get the voltage across VB naught will be 2Vs by 3. So since these VA naught and VC naught are connected to positive, the voltage will be Vs by 3, that is plus Vs by 3, and VB naught is connected to negative, so it is V minus 2 Vs by 3, right? And similarly for the second step, what are the say 60 to 120 degrees? What are the devices conducting means 6, 1, and 2. So here also 6 and 2 are the negative group of device, and 1 is the positive group of device. So we can see 6, 1 and 2 are in closed position for 60 to 120 degrees. Remaining 3, 4 and 5 are in open position since it is not conducting. So the A phase is connected to positive and B phase is connected to negative and the C phase is also connected to negative. So now the circuit will be differing. The equivalent circuit will be differing. So two phases, that is B phase and C phase, will be connected to negative and A phase alone is connected to positive. So the circuit will be like this, equivalent circuit will be like this. So A is alone connected to positive and B and C phase are connected to negative. So using the same calculation, we have to calculate what is the voltage across this branch, that is VB naught and VC naught, and what is the voltage across this branch, that is VA naught. So already we have calculated, if it is set alone, the voltage across this will be 2Vs by 3. If it is a parallel combination, it will be Vs by 3. And here VA naught will be 2Vs by 3 and VB naught and VC naught will be minus Vs by 3. Since it is connected to negative, the magnitude will be Vs by 3 and the direction, that is the sign, will be minus. So VB naught and VC naught are same. That will be minus Vs by 3 of magnitude and VA naught will be 2Vs by 3 magnitude. Similarly, for the 6 steps, we can calculate. So this will be like this. So this is the third step and fourth. For six steps we can calculate and we have to tabulate, that is for 0 to 60 degrees. So these are the conduction angles and these are the conducting SCRs. So what are the devices conducting for the each 60 degrees, and this will be the phase voltages for each 60 degrees. That is Vs first 60 degree it will be Vs by 3 and already we have calculated, that is for first 60 degrees the VA naught will be Vs by 3 and second, for the second step it will be minus that is 2 Vs by 3. VA naught we can see Vs by 3, 2 Vs by 3, and for the third step it will be again VA naught equal to Vs by 3. So that thing is tabulated. So here Vs by 3, so for the next step, that is 60 to 120 it will be 2 Vs by 3 and third step Vs by 3 and the fourth step minus Vs by 3 and the fifth step minus 2 Vs by 3 and the sixth step will be again minus Vs by 3. Similarly, we can fill the table, that is VB naught and VC naught. So we can see for the first step what will be the voltage across VB naught, that is minus 2 Vs by 3, second step minus Vs by 3. Similarly, for Vc naught, it will be Vs by 3, and the second step of Vc naught is minus Vs by 3. So it is filled over here, minus 2 Vs by 3, minus Vs by 3, and it is up to 360 is having filled. And for similarly for Vc naught, the table is filled from the calculated equivalent circuits. So these are the phase voltages. VA naught, VB naught, VC naught are the phase voltages. Similarly, we have to calculate the line voltages. So this thing we have to calculate for drawing the output waveforms, right? So for the calculating the line voltages, VA naught will be VA naught minus VB naught, and VBC will be VB naught minus VC naught, and VCA will be VC naught minus VA naught. So first thing, we have VAB. For first 60 degree, we can see VAB equal to VA naught minus VB naught. So here Vs by 3 is a magnitude for first 60 degree of VA naught. Then VAB naught will be minus 2 Vs by 3. So Vs by 3 minus of minus 2 Vs by 3 will be 3 Vs by 3. So it will be Vs. Similarly, next 60 degree, it will be 2 Vs by 3 minus of minus Vs by 3, that will be 3 Vs by 3, so that will be Vs. And here also VA naught is Vs by 3 and VB naught is Vs by 3. So Vs by 3 minus Vs by 3, that will be 0. And next 60 degree for this, minus Vs by 3 minus 2 Vs by 3. So totally it will be minus 3 Vs by 3. So that will be equal to minus Vs. So similarly, we have to calculate up to 360 degrees. So again, VBC we have to calculate like this. That is VB naught minus VC naught. That is minus 2 Vs by 3 minus Vs by 3. That is minus 3 Vs by 3. That will be equal to minus Vs. Similarly, for VC also we have to calculate. So we can see what will be the nature of the waveform for phase voltage and the line voltage. So the nature of the waveform for the phase voltage will be, it is having three steps in positive, that is Vs by 3, 2 Vs by 3 and Vs by 3. That is three steps of three magnitudes. And in negative of cycle, it will be having another three steps, that is minus Vs by 3, minus 2 Vs by 3, again minus Vs by 3. So the waveform will be of 6 steps. So this will be the phase voltage waveform. So the VA naught will be Vs by 3, 2 Vs by 3, and again Vs by 3, 3 steps for positive half cycle, and again negative half cycle minus Vs by 3, and it is minus 2 Vs by 3, again minus Vs by 3. So 2 pi, it is the 360 degrees, it is finishing its one single cycle. So it will be one positive half cycle 0 to pi, another negative half cycle will be from pi to 2 pi. That is, it is completing its cycle from 0 to 2 pi, that is 0 to 360 degrees. So it is a 6-step waveform for the phase voltage, right? So similarly, we have to draw the waveform for the VB naught. So for that, we have to draw the axis and we have to draw. So this is the VB naught. So VB naught, first it is having the magnitude of minus 2 Vs by 3 and minus Vs by 3. That is minus 2 Vs by 3 and minus Vs by 3. And next one, plus Vs by 3 and plus 2 Vs by 3. Right? So likewise, we have to draw the VB naught. The next one, VC naught. VC naught is having first Vs by 3 plus positive and Vs by 3 negative. So here Vs by 3 positive and Vs by 3 negative and minus 2 Vs by 3. So we can draw it from the tabular column, the phase voltage waveform, or we can predict what will be the nature of the waveform. So here first we have to draw the A phase, that is from 0, that is Vs by 3, 2 Vs by 3, Vs by 3, and again minus Vs by 3, minus 2 Vs by 3, and minus Vs by 3. So this is the nature of the waveform. So positive half cycle will be having 3 steps and negative half cycle will be having 3 steps. So plus Vs by 3, plus 2 Vs by 3 and plus Vs by 3 is the positive step sequence, and similarly it is repeating for the negative step sequence. And this is starting from the 0 point. So obviously the second phase VB naught is starting from the 120 degrees. So this dotted line, each dotted line will be of 60-degree intervals. So the second phase waveform is starting from the 120 degrees. Since for each phase it will be having a phase difference of 120 degrees, so it will be starting from 0. The second phase is starting from 120, and third phase is starting from 240 degrees, right? So from this we can easily predict the nature of the waveform, that is say 3 steps in positive and 3 steps in negative, and we can start it from the corresponding starting point 0 degree, 120 degree and 240 degrees. So if we know the nature of the waveform for the phase voltage, we can easily draw the waveform directly, and from this we can take the table, and from this we can fill the table what will be the magnitude of each waveform for each steps, right? So this is the nature of the waveform, and it is repeating from 120 degrees and it is repeating from 240 degrees. And similarly, we can predict the nature of the line voltage waveform. So it is having for 120 degrees, it is having Vs magnitude, and another 60 degree it will be 0 degrees, and another 120 degree it is having minus Vs, and another 60 degree it will be 0. So we can predict first 120 degree it is having plus Vs magnitude, and 60 degree 0, and another 120 degree it is having minus Vs magnitude, and another 60 degree it is having 0. So what will be the nature of the waveform means it will be a quasi square waveform like this. So first 120 degrees it is having a magnitude of Vs, and another 60 degree 0 magnitude, and another 120 degree it is having minus Vs. So likewise we can draw for the another two phases, that is VBC and VCA. So here also we can indirectly draw, that is it is waveform, first waveform, that is the A phase, that is it is starting from 0 to 120 Vs and 60 degree 0 magnitude, and another 120 degree it is having minus Vs, and another 60 degree it is having 0 magnitude. So this will be the nature of the waveform for the line voltages. So this will be shifted by 120 degree for the second phase, and another 120 degree shifted by for the third phase, that is VCA. So this is the nature of the waveform, and it is 120 degree shifted for the second phase, and another 120 degree it is shifted for the third phase. So it is starting from 120 degree VBC, and VCA is starting from 240 degrees. So this is called quasi square waveform. So square waveform will be of positive and negative, and in between we are having some 0 point. So it is called as quasi square waveform. So for the 180 degree conduction mode, the phase voltage waveform nature is 6-step waveform, and the line voltage nature is quasi square waveform. And we are calculating the RMS value of line voltage, that is we have to calculate the RMS value of line voltage and phase voltage. So this is the formula for the single half cycle, that is the limit is 0 to 2 pi by 3, that is line voltage. We are having the magnitude for 120 degree alone, so remaining 60 degree we are having 0 magnitude. So for the since it is a symmetrical waveform, positive half cycle and negative half cycle are symmetrical, that is same waveform nature. So we have to calculate only for the one half cycle alone. So for 0 to pi it is the time period, and we are having the magnitude only for 120 degrees. So 2 pi by 3 will be 2 into 180 degree by 3, that will be 120 degrees. So the limit will be 0 to 120 degrees, that is 0 to 2 pi by 3. What will be the magnitude? That is Vs. So for calculating the RMS value, we have to square, and if we have to take the square root, that is 1 by 2. So on simplifying this, we can get the root 2 by 3 into Vs, that is 0.8165 Vs. Then next one, RMS value of phase voltage will be VL divided by root 3, since it is the star connected load. So V phase will be VL by root 3, that is 0.8165 Vs divided by root 3 will be 0.41714 Vs. And these are the Fourier series expansion for the line voltage and phase voltage. So from this we can calculate the magnitude of each component, that is a fundamental component or any odd harmonic component. This is n is equal to 135 up to infinity. That is for symmetrical waveform, the even harmonics are 0 and only odd harmonics are present. That is 135 are the odd harmonics, up to infinity will be existing. If n equal to 1, it will be fundamental, and if n equal to 3, it will be third harmonic. Likewise, you have to calculate, that is RMS value of nth component of line voltage is. From this we can calculate. So this term represents the maximum value, divided by root 2 will be the RMS, that is 4 Vs by n pi into cos n pi by 6 will be the maximum value, and divided by root 2 will be the RMS value. So for this we have to calculate the fundamental, means we have to substitute n equal to 1. So 4 Vs by root 2 into pi into cos pi by 6. So that will be 0.7797 Vs. So that will be the RMS value of fundamental line voltage. And RMS value of fundamental phase voltage is divided by, that is, from this we have to calculate, that is 2 Vs by n pi sin n omega t. So this will be the maximum voltage of the phase value, 2 Vs by n pi, that is 2 Vs by fundamental means n equal to 1, so 2 Vs by pi, that will be the maximum value. So divided by root 2 will give the RMS value, so that will be 0.4502 Vs, right? So this will be the three-phase 180 degree conduction mode in inverters. So this is an important question. So for the next class, we can see the 120 degree conduction mode, right? Thank you.